The next talk is a presentation of the paper The Full Reducing Krivine Abstract Machine KN Simulates Pure Normal Order Reduction in Lockstep, which adds to the framework for environment machines developed by Biernacka and Danvy. The authors of the paper are Álvaro García Perez and Pablo Nogueira, and Álvaro will be presenting.
In this talk, we prove properties of an abstract machine, in particular that the machine defines the same strategy than the normal order strategy of the lambda calculus. We prove this result by introducing a semantic artifact that corresponds to the machine and that is better suited for the proof of the property. The correspondent artifact is a reduction strategy in a calculus of closures. As this quote by Crégut shows, the importance of full reduction is widely recognized in the theory and implementation of programming languages and proof assistants. Full reduction refers to reducing the term up to a normal form, that is, a term without any redexes. For instance, this is especially important with nowadays proof assistants with dependent types, which need to reach the normal form of a type in order to implement type conversion rules. The machine we study is Crégut's full reducing version of the Krivine abstract machine, which we abbreviate to KN. In a nutshell, KN takes as input a lambda term that it embeds in a closure with an environment that stores bindings, and uses a continuation stack and tracks the lambda nesting level of the term being evaluated. The machine looks up in the environment the binding of a variable represented by a Bruijn index, pushes the operand of an application onto the stack, retrieves such an operand when the operator is an abstraction and places it as a binding in the environment, reduces the body of an unapplied abstraction by pushing a special symbol on the stack and placing in the environment the lambda nesting level of the formal parameter of the abstraction, calculates the Bruijn index of such a formal parameter retrieved from the environment, reduces the operand of a normal form, which is embedded in a special kind of closure that stores pure terms, and finally flattens the stack into a normal form that is returned when all the symbols in the stack are consumed. KN has been proven to find the normal form of a term when it has some. However, the machine is a first-order transition system that manipulates environments and continuation stacks at the low level, and this format is not ready to deploy proofs by structural induction. Our approach is to introduce a higher-order calculus of closures with a reduction strategy that mimics the machine and that is suited for deploying proofs by structural induction, and later to prove that the said calculus realizes the normal order strategy of the pure lambda calculus. We arrive at such calculus of closures from the ones in the tradition of Crivine's calculus of closures lambda rho. Crivine's calculus contains proper closures made up of a term and an environment. The term uses the Bruijn indices representation, the environment stores closures, and the indices are used to access the bindings in the environment, where positions in the environment start at 0. In the example here, reduction starts with a closure with empty environment. When an application is reached, its operand is embedded into a closure and prepended to the current environment. Then, the binding at position 0 is looked up and retrieved from the environment, and then reduction resumes on such binding. In the better rule of this calculus, the operator in an application is reduced in multiple step fashion to a weak-head normal form. This poses some problems when defining a reduction relation which is purely single step. This issue was observed and fixed in Biernacka and Danvy's lambda hat rho calculus. This variant of Crivine's calculus considers a constructor for closure application that enables the reduction relation to be lifted to the scope of the operator. The calculus also includes an expansion rule that expands applications to closure applications. This mechanism is reminiscent of the apply stage in the eval-apply evaluators in the classical literature in higher-order functional programming. Now, reduction expands applications, reduces the operator if needed, performs better reduction, and then continues to reduce as before. Biernacka and Danvy's lambda hat rho is enough for weak reduction. They give account of both call by name and call by value weak reducing strategies in this calculus. However, it cannot accommodate full reducing strategies. We remedy this by further extending the calculus with a constructor for closure abstraction. We also provide a new expansion rule that expands abstractions into closure abstractions. But before presenting this rule in detail, we discuss how to represent the formal parameter of the abstraction in the environment. In our calculus, a variable is represented by a De Bruijn index, which stands for the relative distance between the applied occurrence of the variable and its binding occurrence in the abstract syntax tree. If the binding lambda is immediately above the variable, then the index is 0. Otherwise, the index gets incremented as the distance to its binding lambda increases. However, if we place the De Bruijn index of the formal parameter in a scope which is nested under more lambdas than its binding occurrence, then we have to adjust that index by adding to it the number of lambdas gone down. Inspired by Kn, we use instead the De Bruijn level of the formal parameter, here overlined, which stands for the absolute lambda nesting level of the binding lambda in the abstract syntax tree. 1 stands for the first lambda, and the level increases if the binding lambda is further down. The advantage of the De Bruijn levels is that they need not be adjusted when placed in the scopes of the term that are nested under more lambdas. In order to use the De Bruijn level, we first decorate our reduction relation with the current lambda nesting level, and then the expansion rule pushes into the environment the current level incremented by 1, since the formal parameter has crossed the lambda. We also add to the calculus a constructor for such levels, and we restrict the environments to either contain proper closures or levels, since this would be enough for the reduction strategy that mimics Kn. When a level is retrieved from the environment, the index corresponding to it can be calculated by subtracting the level from the current lambda nesting level. A new rule takes care of this calculation and embeds the calculated index into a new constructor for absolute indices. Absolute indices are formal parameters of an applied abstractions that are not relative to any environment. We show an example of a reduction sequence in our calculus. The sequence starts with a term with an empty environment and expands the application into a closure application. But now it also expands the operator to a closure abstraction before performing the beta step, which replaces the formal parameter by the operand. Then the sequence goes on as before. We also show how reduction acts on an unapplied abstraction. The abstraction is expanded to a closure abstraction, and later the level of the formal parameter is retrieved from the environment. Now reduction moves the scope to the body of the closure abstraction by the means of a compatibility rule that increments the level decoration of the reduction relation. Combined with the rule for index calculation, this results in the level 1 of the formal parameter being subtracted from the current lambda nesting level, which is embedded as the absolute index 0. Notice that the input term was already a normal form, and that reduction has only performed administrative steps which amount to flattening the explicit substitution in the closure into a term. Our main result is a one-to-one correspondence between the non-administrative steps in our calculus and the steps of normal order in lambda. This correspondence is captured by the commuting diagram here. On the top, 0 or more administrative steps followed by one beta step correspond to the one beta step on the bottom. A substitution function sigma mediates between the closures above and the terms below. The substitution function flattens a closure by performing only administrative reduction. The main technique used in the proof of this result is a structural induction on the derivation trees of reduction judgments, which has been possible thanks to the features of our calculus of closures. In a previous work, we used program transformation techniques to interderive Kn and the reduction strategy in our calculus. Together with this previous work, our main result entails that Kn and normal order perform the same beta reduction steps and in the same order. To conclude, our contribution has been possible thanks to the interderivation techniques and to a judicious use of scopes and levels in our calculus of closures. we have proven a result which is stronger than the known result that Kn finds the normal form of a term if it exists. Our contribution adds to the increasing corpus of knowledge on full reduction. We conjecture that variants of our calculus could be used to prove similar results for other full reducing strategies, in particular for the eager strategies in the call by value family.
Thanks, Álvaro. If you're watching the New York stream in Clouder, you should now see a Q&A link where you can ask Álvaro questions by video chat.